All right, peoples, this is the last of the chi-squared videos. As you know, we've been having a look at checking whether things are distributions, match different distributions, and we've had a look at a uniform and then one that's not a uniform, but you're given the bits. Today, we're going to have a look at what you do when you have something that they suggest is normal or binomial. Exactly the same process, everything's the same. The only difference time to time is there's a little tweak to the HOHA. Or the null hypothesis and the alternative, and there is a little tweak to how you find that expected value column. But after that, you still shove it in the stats bit, and then you run the test. So that is all the same, okay? The only difference really is that one column. So let's get started. All right, so just a reminder of dealing with any distribution. That's exactly the same as you saw on yesterday. So we're going to do the same 6 steps, and some of them I'll gloss over quickly because you've done that before. Now, one of the things I've glossed over lightly and haven't really sort of mentioned but didn't show you how to deal with really is what happens if your expected value is less than 5. And you'll see in the the final problem I'm going to do today, you'll see that happen, and it happens twice. So one of the rules is this, that your magic number is that every expected value needs to be greater than 5. That's to do with just some minimum sample sizes and some stuff you don't need to know, but just make sure they're near over 5. So what we've got here is we've got an original table with here's the age group. There would be some observed values. Don't worry about the observed values, they can be any number. But the expected value here, you've got this problem that, see these ones down the bottom here, they are all less than 5. So what you actually do is you combine them all together. Now, you can only do that if they're actually next door to each other. So for instance, I can't combine them with the 10 to 15 age group. So because they're together, so that's like making them into a single bar on a bar graph. So they're all 3 together, so I make them into a single bar. So all you do is you combine them together. So you still do the expected frequency table, and the last one, category, and you don't need to worry about the 30 plus because you're not loading it into anything, right? It's not like you're loading that into your stats. You're loading the observed frequency and the expected frequency in, all right? And then you just pop them together. Obviously, you're going to line them up in the table, so therefore you would also add your observed frequencies for those ones together as well, okay? Just so they're a minimum sample size of 5. All right, so let's have a look. This is to check if something's normally distributed. Now, the normal distribution, you're going to know a few things. First of all, they're going to say, is it a normal distribution? Second thing, you'll notice that you will have these lovely bars in the middle. In other words, you'll have these ranges, which is what happens in a normal distribution table. Okay, so we've got these ranges, and we've got the number of bottles here. We're going to do a 5% test, if you were in HL, they'd make you find the mean and standard deviation. We are in SL, they don't make us do that, but you might have to do that if you're testing. If you do, please load the data in, midpoint, and the number of bottles into your stats mode. Do one var statistics, and please find the mean and standard deviation there. You have done that in your previous statistics topic, so I do not need to go over that again. It all combines together, remember? IB is when everything comes together. But I'm going to tell you the mean for this is, because I've worked it out, 277.24, remembering that I would have used the midpoint for this because that's what I need to do, it's an estimate, and the standard deviation is 3.4027, okay? So in the SL paper, you'd be given these, all right? That's quite important because it saves you a bit of time. All right, so our first job, now that we've got the table here, is to work out our a null hypothesis, so HO. Basically, the null hypothesis says that the data is normally distributed with a mean of 277 and standard deviation of 3.4, and the alternative is the same wording but just says is not. So the data is not normally distributed, okay, with a mean of 277 and standard deviation of 3.4. All right, so that's the first thing. We also know that our significance level was given to us, and that was 5%. So significance is 0.05. So again, if we draw the graph, we're looking for, if it's up this area, it's more than 0.05. We know it's significant. If it's bigger, it's in the reject pile. So that's good. Now, the expected value from this is the only bit that's different. So expected value from this, what you do is you put this into your calculator. So you use norm CDF. So I'm just going to do, so to grab this, you do norm CDF, because you never do PDF, right? And you put, the lower is 266, the upper is 277, the mean is 277, sorry, 272, and standard deviation is 3.4, and you run it, please. And then you take your answer for that, and you multiply it by how many bottles there were in total. And if you do that correctly, then you should have here, get 6.1786. And for this one here, 10.872, 18.727, 23.06, 20.298, and 20.865. So for each of these, I use norm CDF, okay, from the distributions. You've done that before because we've done normal distribution. These are the lower boundaries all down here. Here are the upper boundaries for each section. You have the mean and standard deviation given to you, and you just run them through. Once you've done that, you need to multiply the answer by the total number of bottles. Okay, so the total number of bottles is when you add up here. When you do that, you will get the expected numbers here. You don't need to round them. They don't need to be whole numbers of bottles. Okay, all right, so that's good. Now, once you've done that, it all goes back to normal. So if you have a look down here, I have loaded this data in. So here is the observed. Here is the expected. I have loaded that into the stats menu. Okay, just as normal. Okay, so that's exactly what you're used to doing. All right, the next thing I do, so that's the next step. The next thing I do is I'm going to run it through, and you've done that before, the chi-squared goodness of fit test. I tell it to find the observed in list 1, expected list 2. It asks for the degrees of freedom. In this case, it is 3 because I think it's n minus 2, but I'll just double check that for you in a second, but it will work it out for you anyway off the list. And then it will run the test. So what this test says is that if you have a look, chi-squared value is 10.69. Okay, that's the calculated value. If you were given the critical value, you can compare them. All right, but we've been given the p-value, so we know that the critical value is 0.05. Our value been given is 0.013. Okay, for 8, etc. So we know that this, so since the p-value is less than 0.05, which it is, we have sufficient evidence. Sufficient evidence to reject the null hypothesis. Now, in English, remember that's the last thing you have to do. That means, what does that mean? The data is not normally distributed. Okay. If you accepted the null hypothesis, then you would say the data is normally distributed. Okay, so same, the only thing different is the expected value. So let's go on to the last one. The last one is binomially binomially distributed. That sounds terrible. Okay, again, I've got some data here. I've been told 5% level. Remember, you can have 1%, you can have 10% as well. I've been given some parameters too. Now, if you remember loading into your calculator to find binomial values, and you'll be using binomial PDF for this because you don't want to accumulate them, you just want those exact numbers. You're asked for n, you're asked for p, and then you're given the x values, and these will be the x values here. All right, good. Okay, so we've got that. So here's the test. Again, same steps. So let's do this. Let's have a look at this. Your HO, so my null hypothesis here is that the data is binomially distributed. We're going to do a bit of that because we've been told with, now you can do this, I often write it this, B, and it's 0.5. If you remember, that's how we write binomial. You could write with a blah blah n of 5 and a probability of 0.5, or you can write it in shorthands. And so the HA, of course, is the data is not binomial distributed, okay, with, okay, that's its parameters, okay. Right, we've been told the significance level, so let's move on to the next screen. So we know that the significance level is 0.05. So again, we're looking if it's less than 0.05, p-value is less than 0.05, or the calculated value is less than the critical value. If you're given that, and you may not be, then we can actually reject the null hypothesis. So let's have a look at this. So what I do here is I'm going to do exactly the same. I'm going to do binomial PDF on my calculator, PDF not CDF, I'm not accumulating these. So I'm going to put the n is 5, I'm going to put p is 0.5, and then I will put each of these numbers in. Okay, so 0, then 1, then 2, then 3, then 4, then 5. I get that number out, probability out, and you can do them very quickly because of course you can just go back and replace the number very, very fast. You can then multiply them by the total number of women. So when you do that, you get the following numbers. So this is 4.6875, 23.4375, 46.875, 46.875, 23.4375, and 4.6875. Now, one of the things you may notice about binomial is that with the probabilities, because it's a 0.5, you'll see that they mimic each other going up and down. So that's quite nice. So that will tell you once you get the halfway, you can usually flip them over. We've got a problem here. Can you see it? And that is that for two of these, they are not bigger than 5, and don't round them. So what we're going to do is we're going to collapse these two categories. All right, so this will now be less than 1. Okay, so we'll put these two together and make that 23. We'll put these two together, and this one again we will collapse these two, so it'll be bigger than 4, or 4 to 5, and it will be we'll put these two together, and that will be 34, and we'll add those two probabilities together, and you will see that in the next table. Good, so here we go. Here is the table that I generated. All right, so you'll notice that I've only got, I've collapsed those categories. So I've got 23, 41, 52, and 34. I've collapsed the expected, so there's only 4 of them. I've put that into, that's stats part of your calculator. Again, I do the goodness of fit test, blah, blah, tell it, hey, list 1, list 2. All right, the calculator doesn't care whether you're normal, uniform, anything. It doesn't give a damn. What it cares and what it's testing is whatever you put in list 1, is it kind of a match for list 2? Are they the same? So that's what it's checking. So if you put the wrong thing in list 2, the calculator will still go, does it fit? So it doesn't know normal or binomial or uniform or whatever. What it knows is what you put into the expected value column. Okay, so we ran that through. So let's have a look at this. We've got a chi-squared critical value. You have a p-value that is 0.3262, blah, blah, blah. All right. Now, since the p-value is larger than 0.05, okay, so thinking about that, that means it's here, all right, then that means what we're going to do, we do not have enough evidence to reject the null hypothesis. Okay, so we don't have enough. So therefore, we can conclude, so the final conclusion is this data is binomially distributed with parameters of 5 and 0.5. Okay, I hope that solves it all. It's a little bit of a long video, but I decided to bung them in because you should see exactly the same process. The only difference is the way I write the null hypothesis changes each time slightly, and also the expected value, and you just need to practice that.